despite having an obnoxious title, one that seemingly doesn't attract the Fourier sense audience, perhaps we'll only see linear matrices towards the end, and we'd rather talk about the applications first. It turns out that most of what I do can be explained just in terms of matrices, and therefore should be very accessible to a very wide audience. So I'm going to start with polynomial identity testing. There's a problem where you say you can give polynomials by circuits. Just have a bunch of variables, a bunch of constants and gates, and a bunch of addition and multiplication gates, which tell you exactly what to do, and the output turns out to be a polynomial. And now you can ask whether a particular circuit computes the zero polynomial or not. Okay? Let's see what, this is an example of a circuit, and let's see what it does. So the addition gate on the left would take the x and the y, which are the variables, and add them up to x plus y. Then the multiplication gate that comes right after it would multiply it with the z. And if you come over to the right side, the y and the z get multiplied to yz, and then you multiply it with a minus 1. And similarly, x and z get multiplied, you multiply with a minus 1. And then those two addition gates add all these three things together. The x plus y times z, the negative y times z, and the negative x times z. So when you add all of those three together, the polynomial that you get as the output is this one, which really is the zero polynomial. Right? You can, this is just the distributivity of addition axiom. Okay? And in terms of size, the size of the circuit is supposed to be the number of nodes, which in this case is 17. I see 5 there, 5 there, 5 there, and then those two addition gates. Right? So the basic question is, given a circuit having n nodes, how long does it take for you to determine whether the polynomial is 0 or not? Okay? And polynomial identity testing is basically saying, can you give me an efficient algorithm for this? Okay. And ideally, you'd like a black box algorithm. What does this mean? This means you don't want to look inside the circuit. You just want to be able to evaluate the circuit at certain numbers, and based on those, based on the evaluations of those certain numbers, you want to know whether the circuit computes to zero polynomial or not. This is kind of hard to hope. What you can definitely do is you can come up with a randomized algorithm that's very efficient. The idea being, if you have a polynomial and it's non-zero, and you try to evaluate it at some numbers, it's most likely going to be non-zero. Right? And so you just decide to evaluate this at randomly chosen inputs, and if it turns out to be non-zero, you're good. If it turns out to be zero, you might be in a very unlucky situation, so you try it a bunch of other times, and eventually you get really good. Eventually you can determine it with really high probability. But so far, there's been no deterministic polynomial time algorithm known, whether it's black box or otherwise.
You choose the number or your field, your final field.
Right. So let's say, so the situation I work in is, we call this algebraic complexity, where we decide that which field and how hard it is to encode the field doesn't matter. We just count the number of additions, multiplications, and so on. So, but over Q, I guess you can.
No, how do you choose a random real number or random rational number?
I guess this is what. You can. So if you want to say, you can say a rational number. You want to choose something random. You can give some kind of bound on the size of the denominator and numerator, and then pick something from random. And this bound can be maybe n squared or n cubed, and that should suffice. Because a polynomial of degree n will have only n roots, and if you take something that's big enough, it should work. And the analysis has been done, and it's not the most easiest thing in the world. And that's why it goes by Schwartz, Sippel, and Lemma. So here are some examples of polynomial identities. This is one that you've seen before. This is just x plus y. When you multiply with x plus y, you get x squared plus y squared plus 2xy. Right? You can imagine how this can form a circuit, how you can get such a circuit. A slightly more complicated one is the binomial theorem. And you can have some more strange looking ones that look like this. X plus y multiplied by x minus y cubed minus x times x plus 2y to the 3 plus y times y plus 2x to the 3. Okay. This, if you expand it out, you cancel everything, you end up with 0. It's not immediately clear, and I don't see a quick way of doing this without just expanding it. There's an even more stranger one, something like Euler's 4-square identity, where you take a sum of 4 squares, multiply it with the sum of another 4 squares, and you can write it as a sum of 4 different squares. Okay. And this was actually used by Lagrange to prove the result that any natural number can be written as a sum of 4 squares. So this is one that's actually been used. But we're going to do a slightly different problem, one that looks similar, but we're going to modify it in a certain fashion, which is we're going to add non-commutativity. We're going to be in the situation where multiplication is not commutative, and the real thing that you should really keep in mind is matrices. And these situations happen pretty naturally. And so in your circuits, we're going to modify it by saying every time you have a multiplication gate, you have to tell me which one is on the left and which one's on the right, because now the order of multiplication matters. That's one change that you're going to make in the circuit. And the other thing we're going to do is we're going to allow inverse gates. So what does an inverse gate do? It takes whatever input you give it and gives you its multiplicative inverse. Right? And if you think about matrices, this can be done. You can take a matrix and give it its inverse. Okay. Now, I'm just going to give an example that really doesn't mean anything, but I just want to show the features of such a circuit. So this particular circuit is supposed to compute x plus y inverse multiplied by z plus x whole inverse. And we'll see this once again step by step. So that first addition gate just computes x plus y. Then that's the inverse gate, and I really don't have a better notation for an inverse gate. We'll just take x plus y and give you x plus y inverse. And then you want to take the multiplication gate, and notice how there's an L on that edge and an R on this edge, which is telling you to put x plus y inverse on the left and z on the right. Okay. Then you add them together with x plus y inverse z plus x, and then you take its inverse to get that. Okay. A couple of things here. One is, in the commutative case, if you ever have a rational function, you can always write it as some polynomial over some polynomial. Okay. And this is something that we've done very early on in our lives, where you just try to clear denominators. The problem with doing something like that in this non-commutative setting is you have to decide which side to multiply on. So AB inverse is not the same thing as B inverse A, and therefore it makes no sense to write it as A over B. Okay? That's not the only thing. You also can't possibly write everything as some polynomial times some polynomial inverse. Even that is too hard, because you have to decide which side to multiply things on. So something like this is what's called a nested inverse. You have an inverse inside another inverse, and you somehow can't get rid of that. But that makes things a lot more complicated in this situation. So you might have nested inverses, but here are some examples of identities in this situation, where, if you remember, we started with, in the commutative case, the first identity I told you was x plus y squared is x squared plus y squared plus 2x squared. That's not an identity in the non-commutative setting anymore, because you have to be more careful about multiplying it. And to multiply it, if you watch carefully, you get the x times x and the y times y, y times y, and the x times y and the y times x. Right? This is now an identity in this non-commutative setting. Okay? Some more complicated identities, like Boas identity. This is supposed to be one that you come across in projective geometry, which is x plus x y inverse x, or inverse, plus x plus y inverse minus x inverse. And you can show that this is 0 just by using formal manipulation. Okay, just by using x inverse, by definition is the inverse of x plus y inverse is by definition the inverse of x plus y, and so on. You just use those formal properties, and you can show that this is actually going to turn out to be 0. Okay. One of those exercises that you do. And here's the main example of something that's not an identity anymore, is xy minus yx is not an identity anymore in this situation. Okay. And non-commutative rational identity test. testing is to say, can you give me an efficient algorithm to determine whether the circuit computes a non-zero rational function? The same question in the commutative case, but in a slightly souped up setting. But here's the first thing that you come across. You say, how do I even approach this? What's one way to decide whether something is an identity or not? What do I test it on? In the commutative case, we tested it on numbers, right? You evaluated at various numbers, and if it was non-zero, it was non-zero. But what do you test this on? And so can you even give a randomized algorithm? To be able to test something, you need some kind of source of non-commutativity. Something where multiplication is not commutative. And what's our main example of such things? Where do you find things that don't commute? Matrices, right? Matrices. And so what you can do is, given the circuit which has all this kind of non-commutativity in multiplication and inverses, you can find square matrices. Okay, let's take them all of the same size. And so whenever you see an addition gate, you can add two matrices. You see a multiplication gate with the left and right specified. You multiply them in that order. You want an inverse, you take the inverse, and so on. Right? So you can evaluate a circuit on square matrices. But are matrices sufficient? Does this capture everything? You see, in the commutative case for a polynomial, this is kind of this is something that's actually not the most trivial thing, but it's not that hard anymore. Is a polynomial is non-zero as a polynomial if you can find some numbers to evaluate it on, so that the output is non-zero. Right? But is the same thing true for matrices in this non-commutative setting? And the answer is yes. Yeah.
So what again your exact definition of polynomial? A zero polynomial?
A zero polynomial. So let's see. So you expand everything that you've gotten out, collect all the terms together, and see if it formally comes out to be zero. See whether it cancels out.
So it's kind of a syntactic definition. It's a definition of syntax rather than semantics. I mean, you just need to follow the rules of
That's correct.
expansion and just see what cancels you there.
That's correct. Exactly. So you can do that whether it's the commutative case or whether it's the non-commutative case, except that takes too long.
In what sense?
In terms of complexity. Like, for example, the binomial theorem, right? X plus y to the n, and you write it as a sum of n terms. But multiplying x plus y, x plus y, x plus y so many times takes a lot of effort. Right? Whereas if you evaluated certain numbers, then multiplying the numbers is much quicker. Because if you have to just do it formally, you have to multiply these all out, then you have to collect all the terms. And a computer is not going to be as smart as us, right? When we prove the binomial theorem, we usually do some kind of induction or something. Circuits don't get that kind of power. But somehow, coming back to this, we're saying now in this non-commutative case, and it's definitely not sufficient to evaluate it on numbers, because then the entire non-commutativity is forgotten. And then you realize you can evaluate these on matrices, and it turns out that matrices are actually sufficient. And this is a deep result in math, which when you work out all the language from back there and put it down to the situation, this is due to Cohn. It's about 45 years old now. Is that a circuit will compute a non-zero rational function if you can find some large square matrices to give us input so that the output is non-zero. Okay. So in some sense, this is saying if you restrict the size of the matrices, it's not enough. But if you look at matrices over all sizes, these have captured all possible non-commutativity. Okay? Something doesn't happen for matrices, it doesn't happen anywhere else. And this is something that, if you've done sufficient amount of linear algebra, you shouldn't be surprised with. Now I'm going to do a certain example of this, and we're going to try and follow this example a little closely to see what the kind of phenomena that can happen. So look at this polynomial right there. X times yz minus zy squared minus yz minus zy squared x. Okay? Now you immediately see, if you put in commutativity of multiplication, yz minus zy is 0. Right? That makes this very stupid to consider in the commutative case. This is clearly the zero polynomial. Okay? But let's see what happens in the non-commutative case when you throw in matrices. Okay? Is this a non-commutative identity? And we just saw that you can test this with matrices. So let's start with 1 by 1 matrices, and 1 by 1 matrices is the same as number. Try to evaluate them, the output is going to be 0. For the same reason that 1 by 1 matrices commute. How about 2 by 2 matrices? Is the output going to be 0 or non-zero if I find? Can I find 2 by 2 matrices that give me something that's 0 or non-zero? This might actually be surprising, but what do you think? Do you think you can find 2 by 2 matrices so that this output is non-zero? You cannot. Whatever 2 by 2 matrices you have for x, y, and z, this is always going to be 0. And one way you can check this for yourself if you don't believe me is you can take x to be just a bunch of just a formal 2 by 2 matrix. x11, x12, x21, x22, y to be that, z to be this. Multiply that all out and see what comes out. You will see it comes out to be 0. But here's a slightly more involved argument, if you can recollect some of your linear algebra, is that yz minus zy has no trace. Trace of yz is trace of zy, right? So that has no trace. And these are 2 by 2 matrices, right? So if it has no trace, then you look at its characteristic polynomial of yz minus zy, which I'm going to call t, is going to look like t squared minus the trace of t times t. Correct? That coefficient is the trace, which is 0. And so that coefficient doesn't exist. And so the only terms in the characteristic polynomial are going to look like t squared plus some number, which means t squared is a scalar matrix. If t squared plus lambda times identity is 0, then t squared is negative lambda times identity. It's a scalar matrix. Therefore, it commutes with everything. Whether you multiply it on the left or the right doesn't make any difference. Okay. And so whether I multiply yz minus zy squared on the right of x, or whether I multiply it on the left of x, it gives me the same thing. So you subtract it, that's 0. So you see, not just is this 0 for all 1 by 1 matrices, it's also 0 for all 2 by 2 matrices. Okay. Even if you don't follow this argument completely, you can always just check this formula. It's not too big either. But you can, and this is what's called Wagner's identity for 2 cross 2 matrices. You can find such identities for any n by n matrices you want. They can get a little complicated. You can find some sort of patterns, but this one is called Wagner's identity for 2 by 2 matrices. But if you put in 3 by 3 matrices, such an argument doesn't work anymore. Okay, the trace might be 0, but then the characteristic polynomial looks like t to the 3. Maybe the term of t squared doesn't exist, but then there's a term of, there's some constant times t and some identity. Such an argument doesn't work. And if you throw in any, pretty much any random 3 by 3 matrices, you will get something that's not 0. Okay? Just pick them at random, don't pick them special. But then here comes the general question. If I just give you some non-commutative polynomial or even a non-commutative rational function that looks like that, how far up the line do I have to go before I find matrices that show me this? Right? Suppose it's not an identity. When do I stop? I try to evaluate 1 by 1 matrices, maybe it's 0. 2 by 2 it's 0. 3 by 3 it's 0. But how far do I go down? And you see, something like this is important to get a randomized algorithm, right? We're trying to get a randomized algorithm the same way we did for polynomial identity testing, which was evaluated some numbers. We're trying to evaluate some matrices, but if you don't know how big the matrices are, how are you ever going to give an algorithm? Right? You want the matrices to be as small as you can possibly be. So that's the big question that we're going to try and answer. And so I'm going to make this little definition. It's going to be very, very informal, but you'll appreciate the informality. So let W of n be the smallest integer d such that matrices of size smaller than d suffice for circuits of size n. Okay? This is the number that we're really going to focus on, and we want to make sure this is as small as possible. Is that clear so far? Yeah.
The really suffice for circuits.
So a priori you're given a circuit of size n, it's going to compute some non-commutative polynomial. Right? To check whether this is 0 or not, you're going to need some large square matrices. Correct? And we don't know how big these square matrices are. So I'm saying D is going to be this. So you look at all circuits of size n. For each circuit, there's going to be a different size of matrices that work. And I want to see the smallest size that works for all circuits. So now that if I know what this number is, and you give me a circuit of size n, I will try D by D matrices as a randomized algorithm. And I know that would work.
But then shouldn't that be greater than C? Like matrices of size greater than D would all work for.
That's correct. Greater than D would all work. But then I'm trying to use as small matrices as possible, right? So it's the smallest number that would work.
I think the question is coming from the fact that it says that matrices of size less than or equal to D will suffice, and if D is the smallest number that will suffice over all,
Yeah.
then matrices of size less than D would necessarily not suffice.
That's correct. It's the same. It's the same. Right? Another way to say this is D is the smallest number such that there exists some circuit of size n so that D minus 1 matrices don't give you the right answer.
Okay.
Is that clear? Yeah? Now you search through all of math and you can reduce this question to a question in invariant theory. And there's very general results on invariant rings due to my advisor Dirksen. And this becomes a question on the null cone of a certain action of SLN cross SLN. And then you see what the results there say and you bring it all the way back down to this language. And you come up with a bound that looks like this, which is pretty big. Okay? But it's still better than nothing. You see, just a moment ago, you didn't have a bound. You just knew you had to put in some matrices, and there was no reason to believe you could. There's no reason to actually. So here's one more thing. There's actually no reason to believe that you have a bound a priori. Right? You take different circuits of size n. You might need bigger and bigger matrices for different circuits. Okay, so this result itself is non-trivial in the sense that it says there's one bound that works for all circuits of size n. And then this was recently brought down to n plus 1 factorial by some computer scientists trying to solve the exact problem. And n plus 1 factorial, I hope I don't have to convince you, is still very big. I usually don't have that liberty to convince, but I think with this audience I don't have to convince you n plus 1 factorial is really big. What we are able to do is we're able to bring this bound down to linear. Yeah.
So this is the title says randomized algorithm.
Yeah.
This is our probability.
Some matrices work, you can't find the matrices, right?
No, where is the randomized get into this result?
So I'm trying to give a randomized algorithm. And so what's the randomized algorithm I'm trying to say? I'm trying to say, look, you have a circuit, you want to evaluate this on some matrices. Right? You want to pick these matrices at random. But if I don't tell you this, if I don't tell you something about the size of these matrices, how do you pick a matrices at random? Do you get that? I need to somehow tell you what size matrices to pick, right? And depending upon the size of the matrices, evaluating the circuit will take that kind of complexity. If I have to pick really large matrices, just evaluating the circuit will take a lot of effort. Yeah.
So the algorithm for computing omega of n is not randomized, right?
No,
It's
omega of n is just a
it's
number.
just-
We're not. Yeah, omega of n is a number.
Okay.
The number is going to help us get a randomized algorithm.
Okay, so the computation of omega n is deterministic.
Oh yes, yeah, okay, yeah. The computation of determinant of omega of n is not an algorithm. It's a priori bound that has nothing to do with the algorithm. The algorithm will now just be, okay, you know how big the matrices need to be, at least. So just plug in random matrices of at least that size. And that gives you a randomized algorithm, right? And so what started with 2 to the big O of n squared 15 years ago, which is clearly not implementable, right? You can't even try to do this. Came down to n plus 1 factorial last year, and we actually just brought this all the way down to linear. And so if the matrices are linear, then multiplying and adding matrices and taking inverse, these are all polynomial operations. And so you actually get a polynomial time randomized algorithm, which is kind of surprising. Okay? But here's something that's even more interesting, is you can actually get a deterministic algorithm, which should really surprise you, because in the commutative, how often have you seen that adding something as nice as commutativity makes the problem harder? How often does this phenomenon happen? Polynomial identity testing, nobody knows a deterministic algorithm. I don't think anybody expects one. But in this case, out of nowhere, you get a deterministic algorithm. But I have to warn you, it's kind of hard to describe this deterministic algorithm. Okay? They're kind of complicated, but they work. So one of these algorithms is you can take our bounds and you can use an algorithm of Gurwitz. What Gurwitz does is he takes a bunch of matrices, comes up with something called a completely positive operator, and he wants to, and then he has some measure of how far it is from doubly stochastic, and then he has some way of trying to see if he can modify his operator to get to this doubly stochastic by series of normalizations left and right. Doubly stochastic has two conditions it has to satisfy. So he tries to satisfy one first, something else will go wrong, then he tries to satisfy the second one, so on. Okay, and these kind of things work in most cases, but they don't work in all the cases. But then once you use our bounds, you can then, whatever situation you have, you can blow it up by polynomial size, and this blow up is polynomial because our bounds are linear, and polynomial bounds will work. And so you can use this Gurwitz's algorithm on this modified data, and that kind of works. Okay. But then what also happened at roughly the same time is these four people, this is Garg, Gurwitz, Oliveira, and Wigderson. They managed to find a better analysis of Gurwitz's algorithm itself, which shows that it kind of converges, and it's kind of interesting, but it's also very hard to explain, and it's completely different. So one feature about Gurwitz's algorithm is it's completely analysis. It works over Q and nothing else. There is no analog of Gurwitz's algorithm over fields that are not Q. Okay, you might extend it to real numbers and complex numbers, but trying to extend it to like a finite field is impossible. The notions just don't make sense. But these guys, they did a better analysis of Gurwitz's algorithm, and they said, actually, you don't need this doubly stochastic process. If you're within epsilon of doubly stochastic, then you can actually conclude it, and so on. And so they came up with this result at roughly the same time. But then a little later, after our bounds, if you remember these people who came up with the n plus 1 factorial bound, they use our bounds to get a deterministic algorithm over sufficiently large fields. Okay, and the sufficiently large is for the same reason. So if you have back to the commutative case, if you have a polynomial, and it's non-zero polynomial, then you'll find some input for which it's non-zero, right? But this is only true if your field has enough elements. If you take, say, the finite field with 3 elements, look at the polynomial x cubed minus x. This is a non-zero polynomial, right? Evaluate it on any one of the 3 elements in F3, the field of 3 elements, you get 0. If you want these two sort of notions to coincide, you need your field to have enough elements. And so that's, you see your algorithm where exactly you need these kind of things, and that's what that sufficiently large will tell you. Okay? I'm a little unhappy with them because, right up to the end they give exact numbers as to how big their field should be, and right at the end they just put an omega. And that's very annoying too. At least for mathematicians, that's very annoying. Okay. But the feature of this algorithm is that it's completely algebraic. There's no analysis involved in it. There are all kinds of other. Oh, yeah, and the other thing is Gurwitz's algorithm will only tell you whether it's good or bad, whether it will tell you whether something is an identity or not. But what this algorithm does is, if it's not an identity, it will find for you matrices that prove it. Not just will it tell you that something is not an identity, it will give you specific matrices that you could input to verify that it's not an identity. And there's a bunch of other corollaries that I might just explain briefly. And this is kind of one that is important in the commutative setting. I don't know how important it is in the non-commutative setting, but it still counts. Is that if you look at the non-commutative determinant, see, determinant is a polynomial. Take an n by n matrix. Determinant is a polynomial in the entries, right? You take your favorite way of expanding your determinant, write it all down, pick some order for each of the monomials. That gives you a non-commutative polynomial. Right? Now, can you give me a circuit that computes this polynomial, and can the size of the circuit be small? And the answer is no. And this comes due to our bounds. Our bounds being polynomial tell you that you can't get a polynomial size circuit. I think we get a lower bound of 2 to the square root of n or something of that sort. Okay? Maybe 2 to the square root of n or minus log n or something. And here's the other thing. So when I say a circuit, I mean the circuit in the non-commutative setting along with the inverses. In the commutative setting, this now it's not that big of a difference because they found circuits that work otherwise too. But like you can find the determinant of a matrix better if you use Gaussian elimination, right? And when you do things like Gaussian elimination, you're inverting numbers. So you're going into rational functions and coming back. And that sometimes makes it easier. Although now they found circuits that don't involve inverses and are still polynomial in size for the commutative case. But in the non-commutative case, even if you throw in inverses, you still can't get a polynomial size circuit. And then there's this entire generalization to invariant rings associated to quivers. I don't know how much I should say about this, but so if you have, perhaps I should leave this to the end if I really want to say anything about it. And recently, these same people, the ones who did a better analysis of Willis's algorithm, they found applications to these things called Braskamp-Lee inequalities, and I'm just going to describe them to you vaguely. So this is a set of inequalities that are described by Braskamp-Lee. And what do they involve? The inputs they take in are a bunch of matrices, and they write two integrals on both sides. These integrals involve these matrices in various ways, and then they stick a constant and put a less equal to. Okay. And several famous inequalities are examples of this, like Holder's inequality, some Brun-Minkowski inequality. Many of these things appear in number theory. I'm not entirely familiar with them either. But it encapsulates a big range of inequalities. And it turns out that you will get an inequality, but you need to figure out what that constant is. And figuring out that constant seems to have, it is connected to this problem. And it's really connected to this problem via quivers. So there's a degree of separation between that problem and this problem that goes through quivers. Quivers are directed graphs, as Suman told us. And when you say quivers, it just has a notion of matrices associated with it, but as a directed graph has a notion of graph theory associated with it. But that apart, it goes through this machinery of quivers, and you can get these results in Braskamp-Lee inequalities, such as you can find these constants up to a high degree of accuracy. You can figure out when that constant is actually not infinity. I mean, infinity will always give you an inequality, right? Something's less equal to infinity times something's always equality. You can figure out when exactly that. So that's something you can figure out in polynomial time. Is when exactly you get a non-trivial inequality. And these guys also give an algorithm that tells you, the best possible constant up to whatever degree of accuracy you want. Now I'm just going to sort of briefly sketch through the proof of how to, what these matrices sort of look like. When I say proof sketch, I mean the linear bound on the size of the matrices. But this is going to be a little bit of linear algebra, so if you can follow it, try to follow it. So given n by n matrices, let's say m of them, x1 to xn, all taken over some field, you create a linear matrix which is just going to be t1 x1 plus t2 x2 plus tn xn, and these ti are just going to be non-commuting independent variables. Just formal variables with absolutely no relations whatsoever. Okay? What's an example of this? x1, let's take it to be this matrix, 0, 1, 0, minus 1, 0, 0, 0. x2 to be this, and x3 to be this. Okay? And I'm going to use for this example at least, I'm going to use A, B, C instead of T1 to Tm. And so the linear matrix that you create will be something that looks like this. This is a parametric version of skew-symmetric 3 by 3 matrices. Okay? What is one feature of skew-symmetric 3 by 3 matrices, you know, or odd skew-symmetric matrices, you know? They have determinant 0. Okay? A skew-symmetric matrix is something that satisfies A is negative A transpose. Okay? So you take determinant. Determinant of A is negative 1 to the size of the matrices, which if odd is minus 1, times determinant of A transpose, which is determinant of A. So then you get determinant is negative of determinant, so the determinant has to be 0. Is that good? So, this linear matrix, if A, B and C are numbers, is always going to be 0. But then we're not taking A, B, C to be numbers or even commuting variables, we're taking them to be non-commuting independent variables. Okay? And in this situation, I want to ask you whether such a matrix is invertible. And this question is what's called non-commutative Edmonds problem. Can you give me an efficient algorithm to decide if a linear matrix is invertible in this setting? Okay, and you might recognize this criterion. I just told you this about 20 minutes ago. Is such a matrix is invertible if you can find some large square matrices that you sort of just plug into those entries and you get this big block matrix. If this big block matrix is invertible, then your initial linear matrix was invertible. Yeah? It's kind of the same. It's kind of the same setup and it's the same criterion actually. And the idea is somehow here, in this situation, it's a lot easier to show that matrices of size n minus 1 suffice. And here's the idea. You say, look, if you have matrices of size k plus 1 that work, then I'll show you that k by k matrices itself work. And here's how you do it. Say A, B, C are k plus 1 by k plus 1 matrices. So let's say k is 1000. Okay? It's easy to do this with numbers. So you found 1001 by 1001 matrices A, B, C that work for you. Take out the last rows of each one of these ABCs and the last columns. Okay? You've effectively removed 3 columns and 3 rows, right? Initially, these were 1001 by 1001 matrices. So this was a 3003 by 3003 matrix and it was full rank. So it had rank 3003. Now you threw away 3 rows and 3 columns. You throw away 3 rows, how much can your rank drop by? 3. And then you throw away 3 columns, your rank can drop by 3. So your rank drops by at most 3. So what you have now is, once you throw away the last rows and columns, is a 3000 by 3000 matrix whose rank is at least 2997. Okay? But now here's a really deep result that I tell you is, if you put in k by k matrices, the maximum possible rank will be a multiple of k. The maximum possible rank. Okay? And what this is really saying is you can basically do block Gaussian multiple. Block Gaussian elimination can be done. It won't be done for any, you might not be able to do it for specific choices of A, B, and C, but for most choices you will be able to do Gaussian elimination. Blockwise. And this is perhaps the deepest result in math that I've seen in recent times. That's completely been forgotten. Mathematicians don't know this very often. Okay? But anyway, so what does that tell us in this situation? So we had this 1001 by 1001 matrices that you plugged in to get full rank, so that had rank 3003. Then you threw away 3 rows, 3 columns, so now the rank is at least 2997. But now it's as if you plugged in 1000 by 1000 matrices, right? The maximum possible rank must be a multiple of 1000. You know the maximum possible rank has to be at least 2997 because we had one example of that. So what must the maximum possible rank be? It has to be 3000. Okay? And if you see, that's where somehow the deterministicness sort of disappears. I can't tell you how to find those matrices. Right? I tell you the maximum possible rank is this. In fact, you pick up random you just pick up randomly chosen matrices which will work, but these people actually tell you how to find them. So the ones I'm talking about, yeah, so this algorithm that I'm talking about tells you how to do this efficiently. So that's kind of the idea. And actually that simplistic idea will not get you all the way down to n minus 1, it will get you down to n plus 1, but I don't think you get beyond that. After that you need a little bit of, we like n minus 1 because it makes some of the numbers look nice for us, but those numbers are not things that you might be interested in. Okay. But, so here's how the problem works. So you give, so if you give me a circuit of size n, I will create a bunch of linear matrices. Okay? And in fact, I can tell you how many I will create. I'll create one for each inverse gate. Because inverse gates are really where the trouble happens. Okay? And in particular, notice this is not going to be a black box algorithm because I already have to look inside my circuit to make these linear matrices. Right? So it's not black box, and I don't think there's any reasonable approach to a black box algorithm yet. And then what the previous slide showed was once you're in this situation, it's enough matrices of size linear work. Okay, so let's stick to linear. So matrices of size linear in n suffice for testing invertibility of linear matrices. And so consequently, matrices of size linear in n suffice for rational identity testing. So this creating a bunch of linear matrices, this was done by Pavel, Krug's and Ivy Wigderson. And what they also say, not just do they create a bunch of linear matrices, they say this circuit computes something non-zero if all these linear matrices are invertible. Okay? It's kind of, there's actually a similar result in the commutative case where, and this is Valiant, is that how you say his name? Yeah? He says if you give me a circuit for commutative polynomials, I'll create for you a matrix with the size, globe-only polynomial, whose determinant is the polynomial that your circuit computes. It's the same kind of question in the commutative setting. Okay, and the same sort of proof, same sort of algorithm going from circuits to linear matrices works in the non-commutative setting, but it's actually a lot more involved, and it requires some kind of analysis and derivatives and things. And so anyway, so we do this, we take a circuit, we create a bunch of linear matrices, you can test the invertibility of those linear matrices with linear size matrices. And so you know that matrices of size linear in n suffice to test rational identities. And in fact, you can use this algorithm by these computer scientists. Ivanios, Jimmy, I don't know how to say his last name, and Subramanian. But their algorithm requires additional criteria for invertibility. And this additional criteria comes from the theory of quivers, and it's one that I really can't find a simple explanation for. But here's the criterion. I can tell you the criterion very quickly. So you have these bunch of matrices. I can tell you that this linear matrix is not invertible if you can find a shrinking subspace. So a matrix is a linear transformation from a vector space to a vector space, right? If you can find a subspace of this vector space so that the image has smaller dimension, that's called a shrinking subspace. Okay? And if something like that happens, there is no hope of anything inside there's no hope of this being invertible. This is very easy to see in the commutative setting, but it also works in the non-commutative setting. Okay? You sort of shrink a subspace, you can't possibly have it be a bijection in between subspaces. So that's the kind of criteria that comes from theory of quivers, and I don't see a simple explanation for that. Here's some bibliography. These are papers by me and Wilson. They're all up on archive. They might be written in the language of quivers mostly. You can also look at the papers by Garg, Hurwitz, Olivier, and Wigderson. This is going to be a lot of analysis, which might not be the easiest thing to read, but I think Wigderson is really good at writing introductions. And particularly this paper has an introduction that's like 20 pages long, where he explains as you can see, this problem has several ways. You can look at it from quivers, you can look at it from linear matrices, you can look at it from identity testing, and he puts together all those different views and tells you how they interconnect. And so that's a really good place to read some kind of introduction to this problem. And this is the recent paper on cross cantilever inequality, which also says something, but it's not as introductory. And this is the results on by Ivanov, Jimmy, and Subramanian, which is their algorithm, which is a completely algebraic algorithm. Any questions?
When you started talking about non-commutativity, I naturally thought about quaternions, and then if I think of extensions of quaternions, I think about Clifford algebras. So are there similar theorems about the size of Clifford algebras we might have to use to determine whether there are identities?
I'm actually not completely familiar with Clifford algebras, but I would say, the one thing that really bothers me is, do quaternions encapsulate all of non-commutativity?
Pardon?
Do quaternions encapsulate all of non-commutativity? There might be identities that are satisfied by quaternions, right?
Quaternions are small,
Right.
but Clifford algebras can be arbitrary, like matrices can be arbitrarily large.
Right, but there still might be empirical relations satisfied by all Clifford algebras. That does not have to do with it. Unlike, and it is possible, I have to look at it. I've never worked